And as far as I know, there's no better algorithm for broadcast search than that. So I'll show you all the details later on tomorrow or today how to do that efficiently. So that's basically broadcast search for you. Broadcast search uses lots of bandwidth because if every node is once a minute asking 1,000 nodes, that means you will also every node will get 1,000 search questions per minute. It's compared to distributed hash tables, it's a little better at doing complex searches like engine yard and near form not doubling. Stuff like that is slightly easier to do on a broadcast search than on a distributed hash table. And on a broadcast search, you can actually use something with expressions. Regular expressions. You can easily do regular expressions on a broadcast search. By doing that on a distributed hash table, sounds it seems hard. So you can do very complex search stuff. Like you have the search horizon. Okay. Any questions about that? Okay, distributed hash tables. How many here think they know what a distributed? Well, how many here think they don't know what a distributed hash table is? I'll do an overview anyway. Basically, we connect all the nodes. Each node gets an address, and then we connect them in a big ring. And when we publish a piece of data, for instance, a movie, that's not the best example, but let's use that example. We don't send, for instance, if the movie is named motorbike, you don't put the movie in the node name M. You just send a little message, a little address package to this node. So that tells that if you're looking for M, there is a node that has motorbike. So it might be this node that has the film, but here there's a link, so to speak, to that in the case of just a database field. So any node that wants to find motorbike, they look at M and ask, is there any mention of motorbike? Yeah, there's one file over there. You connect to that one and fetch the file. Or actually, normally it's the name of this file sharing form, so you can download it. Let's see what we'll go to. Okay. First of all, we can't have one node for each address because perhaps we just have 1 million nodes, but there are more possible names than that. So the data is stored in the closest nodes. As you see, this is responsible for a span from M to P. Also, neighboring nodes are backing this one up. If this one disappears, they should have a copy of the data, because then the search request will end up in the closest neighbors. So they're backing each other's up. And that's actually one of the hard problems to do correctly. We'll go on that later.
So one question for you. A list or a ring has a natural order.
Yeah.
Does a hypercube have a natural order?
It does.
Does it?
Yeah, because the hypercube has an address space. I can show you it. Let's see. That's a good question. Hypercube, if you look at the one-dimensional hypercube,
yeah,
it's two nodes. It's nodes 0 and 1. If you extend it to two-dimensional one, then you have nodes 0 and 1. Actually, 0, 0 and 0, 1, and that's 1, 0 and 1, 1. It's binary math. So they have addresses, and as you extend it, for each extra dimension, you get 1 bit more address.
Okay. So you're binary order.
Yeah. So it has one. Hypercubes, we use them as a routing overlay on these tables, and we use them because when you have a target address, and you can simply compare it with your own address and take any bit that doesn't match and send a message to one of your neighbors that has that bit set. So you actually have several ways to route messages here. So it's very simple to route around problems like that. But we'll get more into that later. Okay.
Yeah.
Let's see, where were we?
Should we break off?
What to do?
We might go because there's a slot for us to get some lunch.
Yeah.
Do you want to continue for a few minutes?
I can just say one thing more before we go. Of course, going around the ring is very inefficient, so we have shortcuts across the ring. We have lots of links in some smart manner, and those links that we can find in a shorter path, these links are the routing overlay. That's what we call it. So that's. Well, then you can stop there.
Just a question on that. When you scale the amount of data that you're handling and the amount of nodes, is there a natural way to deal with that? Like the Dynamo stuff deals with it by making these virtual nodes where they're a lot smaller, and each node manages a whole bunch of.
You don't need to do that. There's other ways to do that.
Okay, so you can evenly distribute it efficiently.
We have to, as you see, the data tends to cluster up because we used to call that the Britney problem, because back then Britney Spears was the most famous one. So there were too many Britney Spears files in the database, and that's so the core node that we're handling B just got flooded. And how to handle that, we'll talk about. There's lots of tricks and methods to spread the data out in the smart way, and we'll talk about that.
That's the usual problem.
I have another name for that now. I don't remember the names. For me, it's still the Britney problem.